Hi, I'm Soc1. In this video, I'm going to explain how we design complex electronic systems like smartphones using SoC. SoC means System on a Chip. Basically, it's an IC that integrates all the components, almost everything needed for an electronic system. For example, iPhone 15. iPhone 15 has been designed using a complex SoC called A17. It's pretty complex. It demands more than 19 billion transistors. A17 has been designed using 6-core ARM CPU, 6-core Apple's GPUs, 16-core neural engine. There could be various other processors like DSP, image processor, and accelerator. Also, there could be various complex interfaces like USB. That's why it demands more than 19 billion transistors. TSMC manufactured this chip using 3nm technology. All right, let's explore the SoC architecture in this module. Let's understand the electronic system. You consider any electronic system, it's composed of both hardware and software. For example, smartphone. Smartphone is very different from devices like desktops. So we expect smartphone to be highly portable device. At the same time, it should consume very less power. So there are three things important for smartphone: power, performance, and area. Power. It has to consume very low power. Performance. Consumers like you want to run multiple applications in parallel. You think of your life. You will be using smartphone for various things. You use your smartphone to book a cab using Uber. Then while traveling, you might want to check your status on Facebook. And then your friends might call you. Or you might want to check some WhatsApp messages. And then you may think about editing your resume. So like this, you would end up running multiple applications sequentially. But all these applications are going to run in parallel. You will never think something like, okay, let me kill this application. I booked the cab. Now I don't want Uber. Now I want to edit my resume. So I'm going to use Word doc. You're not going to kill the application and then you're not going to invoke something new. So all these things are going to happen in parallel. That's why performance is very critical. So to improve the performance, what we do is we use multiple processors like CPUs, GPUs, DSP. When it comes to CPU, there could be various kinds like RISC reduced instruction set computer. We use RISC processor primarily for smartphone, but we prefer CISC complex instruction set computer primarily for desktops. Also, we need GPUs because we want to play video games. And there could be other processors like DSPs, image processors, accelerators. For applications like facial recognition, we need neural engine. So we make sure that the chip is built with multiple processors, different kinds of processors. That's how we try to increase the performance. Also, when it comes to designing the processor, we make sure that we use multiple cores. It's always going to be like multi-core processor. In the case of iPhone 15, it has been designed using 6-core ARM CPU. So we need multi-core processor. When you run multiple applications, different applications will be running on different cores. Each application will be considered as thread for the operating system. We will explore it a little later. So performance is critical. Power. Though we run multiple applications, still we can't expect the smartphone to consume so much power because it's a battery operated device. So we need to design the chip in such a way that it consumes very low power. We follow certain methodologies like low power design, low power verification to make sure that the chip consumes very low power. We will also explore low power design methodology a little later. So power consumption. It has to consume very low power. Area. We make sure that the chip consumes very less area. So what we do is we try to optimize the design. That's where we follow different techniques in digital, K-map. So we try to reduce min terms. On top of it, we use EDE, electronic design automation tools, various algorithms to optimize the design further. That's how we try to reduce the area. Also, we prefer higher technology nodes like 3nm. iPhone 15 has been fabricated using 3nm technology. So the technology is critical. What we do in VLSI is we try to reduce the size of the transistor. If we can reduce the size of the transistor, we can pack more and more transistors. You think of smartphone. This is how you can visualize the hardware. Look at here. You need processors, various kinds of processors, multi-core processors. You need memories, different kinds of memories like registers, random access memory, primarily read-only memory. We try to pack read-only memory as part of the chip. Generally, we don't pack the RAM as part of the chip. So read-only memory, like flash. And there could be various interfaces, how the chip can communicate to the external world. Think about it. We need various kinds of interfaces like UART, SPI, I2C, JTAG, USB. So we use various kinds of IPs, intellectual properties, to realize this kind of complex SoC. When it comes to realizing a smartphone, what we do is we try to integrate almost all the hardware components as part of the chip. That's why it's called system on a chip. We try to realize the entire system on a chip, single chip itself. So why we prefer system on a chip? It helps us to achieve our PPA goals, power, performance, and area. Now let's look at the software. There are various layers like application software and system software. Application software. For example, you look at smartphone. There could be various apps like LinkedIn, Twitter, Facebook, Gmeet, YouTube. Software programmers prefer higher level languages like Java and Swift to create these apps. But when it comes to running the applications, what we do is we convert the applications into machine language. Think about smartphone. Every time when you install an app, what happens is you are downloading the binary. What is that binary? That binary is nothing but machine language. Machine language is based on the processor we use. In the case of iPhone 15, we use ARM processor. The processor could be ARM or RISC-V. We prefer a RISC, reduced instruction set computer for smartphone. Machine language depends on the ISA, instruction set architecture of the processor. We use various tools. It's called tool chain. Tool chain includes various tools like compilers, assemblers, debuggers. The compiler converts the high-level language like Java or Swift into assembly language. When I say assembly language, in this case, it's ARM assembly. iPhone 15 uses ARM processor. So everything will be converted into ARM processor instruction. We also use assembler to convert the instruction into binary. Binary could be 32-bit or 64-bit or 128-bit. The binary depends on the register width of the processor. So you look at the ISA, it provides various options like you go with 32-bit processor, or you go with 64-bit processor, or you go with 128-bit processor. It completely depends on the register width. Most of the processors use standard registers like GPRs, general purpose registers. But when it comes to smartphone, as a consumer, you think about operating system. So you classify the smartphone like 64-bit smartphone. So what it means is the smartphone uses 64-bit processor. So every time you download any application, what actually it means is you are downloading the machine language of that particular processor. So all the applications have been converted into binary, and that's what you download from the App Store. That's about application. Now let's look at the system software. Application can't work directly with hardware. It doesn't have permission to deal with hardware. So we need a special software called operating system kernel. Operating system acts like supervisor. Basically, operating system manages the complete hardware as a supervisor. Operating system also includes device drivers and stacks. Let's look at how it works. You consider any hardware. This is how you can visualize. There could be various hardware components like read-only memory, flash. We prefer read-only memory to store softwares like firmware. And it has CPU platform. We prefer multi-core CPU because we need more performance. Every CPU has general purpose registers and special registers. There could be various cache, various levels of cache, L1, L2, L3, to improve the performance of the processor. That's how you can visualize the CPU platform. It will also have other things like core level interrupt controller, platform level interrupt controller. And there is another important component called RAM, random access memory. Every time when you invoke any application, basically the operating system loads the application in the RAM. And the hardware will also have storage device, something like SSD. It could be hard disk. Hard disk or SSD, it will have everything. Bootloader that can load the operating system itself, and applications. So here, everything is stored in terms of machine language, binary. And whatever the data you generate, you might be using applications like Word doc, you might be editing your resume, you might be dealing with some Excel sheets. Everything is stored as binary. That's your data. And there will be free space. And OS will also use some space as swap memory space. Let's look at how it happens. The system booting. When you put on power, CPU executes firmware. Execution is going to start off with firmware. Firmware is called machine mode software. Again, we classify the software components into machine mode. Machine mode is the highest privilege mode, supervisor mode, the next privilege level, and user mode, the least privilege level. CPU defines the privilege levels. Machine mode software means this kind of software will have complete access to the hardware. So here, CPU executes firmware. It's a machine mode software. What it does something like post power on cell test. It's going to check everything on the hardware platform. It will also check the peripheral, whether everything is working fine, power on self test, and then it will point to bootloader. Now, the CPU executes bootloader. What the bootloader does, it loads the operating system kernel. Operating system has various layers. It has some assembly code. Generally, it's called as entry.s, and the kernel itself, and device drivers. If there is going to be any external interrupt, how to deal with it. Device drivers take care of it. After loading the kernel, the execution is going to start with entry.s assembly code. Here the execution is going to happen in the machine mode. So far, the execution has been in machine mode. Everything started off with firmware, machine mode software, then bootloader. Bootloader was running in machine mode. Now the bootloader loaded the operating system kernel. Still the execution continues in machine mode. But we expect the operating system to run in supervisor mode because we expect the operating system to be the supervisor of the complete hardware. So entry.s does the job. It actually does everything for the kernel execution. So it creates the execution environment for the kernel execution. What is that? Software programmers use languages like C, C++ for the OS kernel. So for the execution, it has to create necessary stacks. So that's what entry.s does. It allocates the stack. Also, it changes the mode from machine mode to supervisor mode. So entry.s points OS kernel now for the execution. And the mode is changing from machine mode to supervisor mode. Now the CPU executes operating system kernel. So the operating system is going to happen in supervisor mode. And during the execution, the OS kernel manages RAM, random access memory. So it uses registers like SATP, Supervisor Address Translation Protection Register, to deal with RAM. What it does is it defines various pages. That's how it's going to deal with multiple applications in parallel. Every time when you invoke any particular application, it will be loaded into that particular page. So here each application will be executed as a process on a particular CPU core. That's what the operating system does. So it is managing the complete RAM in terms of pages. And every time you invoke any particular application, the operating system loads the application into memory. And that's how the execution happens. Now let's look at how the operating system manages multiple applications. Here, I'm showing some more details like interfaces. There could be various interfaces like SPI, UART, USB, GPIO, PCIe. And there could be components like platform level interrupt controller. When you invoke any particular application, operating system loads the application. The application will be loaded and it will be executed in the user mode, least privilege mode. Application will not have any permission to access any hardware directly. It has to happen only through operating system. So how the processor executes the application? Look at it. Let's say I invoke calculator. What happens? When I click on calculator, the operating system loads the binary machine language of calculator into RAM. So in this case, it's going to happen in page 1. Now the binary is available. Everything is in 64-bit. For example, if the smartphone uses 64-bit processor, then you can expect the machine language to be in 64-bit. After loading the binary, now it's available in page 1. The operating system sets PC, every processor, every core, as a special register called program counter. So the CPU uses program counter to fetch the instructions from RAM. So the operating system takes the starting address of this page 1 and it loads the PC with this address. Using this address, the CPU is going to fetch the binary. Binary is nothing but instruction. It's going to fetch the binary from the RAM sequentially and it's going to execute. For example, I do something like 2 plus 4. What it does is it gets the operands 2 and 4 and it does addition. So CPU has arithmetic logic unit. It adds the values operands 2 and 4 and it produces the result 6. That's how it works. So every time you invoke any particular application, the operating system loads the equivalent binary into RAM, and then the operating system takes the starting address of that binary, then it sets the PC with that address, then the CPU uses that particular address to fetch the binary instructions. Binary is nothing but instruction. The CPU is going to fetch the instructions sequentially, and then it's going to execute. It doesn't have to be sequential. It could be even non-sequential also. If there is any if-else, then obviously it's going to change the execution flow. That's how the execution happens. All right. So the user will run multiple applications in parallel, but there could be various scenarios. Think about it. What if the application wants to do something directly with the hardware? For example, if the application has to create some file, or if the application wants to kill some process, existing process, whether the application will have permission. It has to happen only through operating system. This is one scenario. Let's say you do something like make directory as a user. You want to create a directory. Then in that case, how it should happen on the disk, operating system has to decide, right? The other scenario could be, what if something wrong happens with the application? It could be an illegal instruction. We are running the application on ARM processor, but it uses the instruction of RISC-V processor. What would happen in this case? Or if anything happens like divide by 0, what to be done? The third scenario could be handling the interrupts. Things are happening. You're running multiple applications and then suddenly you feel like you want to connect SD card and then you want to download some photos. In that case, how the operating system can deal with external interrupts. Look at here. So the user is running multiple applications. It's going fine. And then there could be some interrupt, external interrupt from USB. Operating system kernel receives the interrupt and operating system executes trap handler. So operating system maintains C code to handle the trap. It's called trap handler. So operating system executes the trap handler. As I mentioned, OS kernel has device drivers. So in this case, the operating system identifies, okay, this is the interrupt from USB. So it will make use of the USB device driver. And using the device driver, the CPU will configure the interface, whether it is host or device or hub. Based on the device you connected, the CPU is going to configure the interface and then it will enable the data transfer. And once it completes the data transfer, the same trap handler, now it will update the operating system kernel to resume the interrupted thread. For example, if this is going to happen on a particular core, like core 3, there was something going on, a particular thread was going on that was interrupted, and then the operating system initiated trap handler. Trap handler now executes the interrupt on this particular core. After completing the execution, the trap handler updates the OS kernel and then OS kernel will resume the previous thread on the same core, interrupted thread. That's how it handles any interrupt. This is how you can visualize the execution. So in any electronic system, you can expect both hardware and software. To realize devices like smartphones, we prefer system on a chip. What it means is we try to integrate almost all the components needed for smartphone as part of SoC, system on a chip. There could be various software components like application software, system software. We have seen the booting process, how everything happens with firmware, and then how the operating system manages the complete hardware. Basically, operating system is the supervisor for the hardware, how it manages various applications, how the operating system manages the RAM. And the most important thing is everything together, application software and system software, everything together, we convert them into machine language. So we use toolchain to convert the software into machine language. We use compiler to convert the software into assembly language. Assembly language is nothing but processor instruction. And we use assembler to convert the assembly language into machine language. Machine language is nothing but binary. Binary could be 32-bit or 64-bit or 128-bit. It depends on the processor. Processor is the one that decides what kind of operating system can be executed, what kind of operating system is preferred for a particular device. Most of the smartphones might use 64-bit operating system. What it means is the processor could be 64-bit processor. So if the processor is 64-bit processor, then every instruction will be converted into 64-bit binary. That's nothing but machine language. All right?